Now we'll take a look at what is famously known as the motor effect. Now, the motor effect is a fancy name that really is examining the force on conductors that carry current in magnetic fields. So over here, we have a conductor. This line represents a wire. It is carrying current, conventional current I, to the right-hand side. It is in this green field, which represents a magnetic field. And what we've basically found is that if you have a wire like this, carrying current in a magnetic field, then this wire will experience a force. That's what we're saying. All right. Well, if we're saying it will experience a force, there are really two main questions as always. If there's forces involved, it is a vector. And if a vector is involved, it's going to have a magnitude and a direction. The magnitude, well, we can give you the formula. And the direction, we can give you a way to do it. So here's the thing. The magnitude is equal to F equals BIL sine theta. For simplicity, theta here is 90, but we'll start to get into that a little bit now. And the direction, you might be surprised to know, is also the right-hand palm rule. So this is where you might want to start thinking about, why is that the case? So we've said, what exactly are we talking about here? We're talking about the motor effect. And what exactly is the motor effect? It's saying that if you have a conductor, and this conductor is carrying current, then it will experience a force as long as it's in a magnetic field. So let's think of our conditions here. You need to have a current carrying conductor. So it needs to be a current. It needs to be in a magnetic field. So if you have a current in a magnetic field, the current must flow in a conductor. Otherwise, where else will the current go, I guess? And then that will result in a force experienced by the conductor. Okay. So the prerequisite is a current in a wire, the wire in a magnetic field, and then you're done. Then you get your force. The force is equal to BIL sine theta, as we discussed, and the direction is curiously the same as before. It's the right-hand palm. That's nice and easy. You might want to think about why that is the case. And if your brain turning on that. But in the meantime, let's define what each of these things are. So F in this case is the force experienced by the wire. And because of the force, it's measured in newtons. B is the magnetic field strength, or magnetic flux density. Or most correctly, it's the magnetic flux density. And that is measured in Tesla. I is the current. Remember, it's conventional current, measured in amperes. L is the length of the wire, the conductor in the magnetic field. Needs to be in the magnetic field. If it's not in the magnetic field, it's not going to experience a force, and that's measured in meters. Now, theta is an angle, and it's the angle between the magnetic field and the current. So let's now take a look at some examples where we focus firstly on getting the direction of the force on these wires. So remember, our rule is very simple. It's the right-hand palm rule. That means you must use your right hand. The thumb must represent the direction of the current. Your fingers must represent the direction of the magnetic field B, in our diagrams, green. And then your palm is going to push in the direction of the force. So for this question in the top left, your current is to the right. That means your thumb is going to point to the right. Your magnetic field is into the page. That's what these crosses mean. That means your fingers point inward to the page. That forces your palm to point upward. So that tells us that the magnetic force on this wire is going to push this wire upward. Taking a look at this example here, we now have the magnetic field coming out of the page. That's what those dots mean there. And that means now we've got the current going downward. So it's going down the page, your thumb is pointing down. But your fingers need to point out of the page, which therefore means they're sort of pushing in towards you. And with that orientation, your hand is now being forced to push to the left. And that gives you this situation here. Now, over here on the third one here, we've got the magnetic field going to the right, so your fingers are going to go to the right. Your thumb is going to follow the current direction, which is going up the page, which then of course means that your palm is forced to push inward. So if anything, that means your force is sort of into the page. It's into the page, inward. Think of it like 3D, it's being pushed in. And because that's rather cumbersome, usually you won't get questions like that. Usually you just get it drawn like this, and so you end up with a force that you can draw quite easily. As a word problem, that will be fine, but as a drawing, it'll be very awkward to draw a force inward. Okay? Here, very similarly, just remember everything is perpendicular to each other. Okay? So if you've already used up 2 perpendiculars on this plane, then the third one must be out of this plane, perpendicular to this plane. So this one, you've got the current going to the right, and your magnetic field is going down. So if that's going to the right while your magnetic field is going down, that then again, well, forces you again to push inward to the page. And so your force again is going to be into the page. So you'll notice in all situations, all of these things are perpendicular to each other. So here are 2 more examples with diagrams which may confuse some of you, but it's not really as confusing as it might appear. Over here, we've got the green line again representing the magnetic field, represented by the letter B. And what we do have here is a cross, which we understand means into the page. And here we have a dot that indicates out of the page. Now, around this cross and around this dot, we have a circle. So this circle here, that I'm going to outline here in blue now, this is just representing the fact that this is the wire. So this is the wire itself. So that cross and that dot is actually representing the current now. Taking a look at this one over here, we now have the perspective of the current being into the page, and the magnetic field is going to the right. So if your thumb is going into the page, because it's a cross, and your magnetic field is going to the right, that means you'll end up with your right hand push rule telling you this is downward. Fingers to the right, thumb into the page, palm down. On this side, you've got the current coming out, thumb coming out of the page, fingers down, which then results in push to the right. So those are some different views of the same scenario. Now we'll take a look at some scenarios where it might appear that the conductors are not entirely horizontal or vertical, and we'll give you an angle of 45 degrees here. Now, these ones appear tricky, and we need to talk about these, but they are not as hard as they appear. So, firstly, we need to find out the angle. The angle here, you're told, is 30 degrees. But the question you really need to ask yourself is, what is the angle between the current and the magnetic field? Now, the magnetic field is going into the page, and the current is going diagonally up the page. So if you try to use your right-hand palm rule on this question, you're just going to need to make sure that your fingers are pointing into the page, as usual. Your thumb is pointing diagonally across. And kind of like when we were doing the circular motion, that your palm does not have a problem with this. Your palm will simply follow this line and give you a direction that is perpendicular to that. And so as far as the direction goes, keeping the color scheme consistent, let's stick with red. That is going to be the direction of the force. Your force is going to go directly perpendicular to the wire. In this case, you're going to have a magnetic field that's going out of the page. So your fingers are pointing out. And because of the fact that you're going diagonally up and to the left, that means your force is going to push directly this way. And that is your force on these wires. So the forces are still perpendicular to both. Let us now examine a scenario like this, however. The magnetic field is going to the right. The current is going here 30 degrees to the horizontal. And in this case, if you try to use the right-hand palm rule on this, you may find it difficult to do because your fingers are trying to go to the right. But if your fingers go to the right, you can't really get your thumb to point in the diagonal direction while your fingers are going to the right because, well, I guess the problem is your thumb is meant to be perpendicular to your fingers, but this eye is not perpendicular to the B, which is a bit of a problem. And that you only have that problem when they're not perpendicular to each other. So there's a few ways you can deal with this. But one way to think about it is this current is going up and to the right, which means you can think of it as the current that is perpendicular to the magnetic field. It's a component, right? You can think of it as a vector. The current is going up and to the right, so you've got one that's going up, and you've got the current that is parallel to the magnetic field. Now, you do not need to worry about this. You can just discard this. Because basically, if you have a magnetic field that is parallel to your current in a very straightforward scenario like this, there's no force. If you have something like this, you don't need to worry about it. The force equals 0 in this scenario. So you're really always wanting the current that is perpendicular to the magnetic field. And if you've got a situation where it's not entirely perpendicular, but only part of it is perpendicular, then just get the part that is perpendicular. Don't worry about that's parallel. And that's, by the way, where your sine theta comes from. Because if this is theta, which it is, then you can see that the sine of this theta is going to be opposite over hypotenuse, giving you the perpendicular component of the eye. So rather than just memorizing what theta is, I think it's better for you to understand why you want to sine theta. And the reason why you want to sine theta is basically because you want to find the components of current and magnetic field that are perpendicular to each other. And that's where the sine theta comes in. So if they're not perpendicular to each other, then draw the components and then just treat this current, which is going diagonally up, as just going up directly. Don't care about the parallel. It's going up directly. So if your current is going up directly, while your fingers are for the magnetic field is going to the right, that then results in a force into the page. So you've got a force inward. And now we come to a curious result. Out of all the questions we've done, this one was the only one that we've said so far where we need to worry about this theta and think about this parallel and perpendicular. If you take a look at these questions, it's very obvious that they're perpendicular to each other. And here as well. But we did these ones as well. And it might not be so obvious that they're perpendicular to each other. And it looks like they're not perpendicular to each other, actually, at first glance. Because we've got this thing going at a slant, and this is going at a slant. But we didn't have any problems. And why did we not have any problems? Even though the wire was slanted. And the reason for that is because actually the current is perpendicular to the magnetic field in these situations. Even though you might not think it is, they are perpendicular to each other, which is why we don't need to worry about the theta in those situations. And this is why in all the earlier examples I gave, I said, don't worry about theta, theta is 90. But the question is why? Now, if you can't, have a little think about it. But if you're having trouble seeing why it is 90 degrees, what I highly recommend you do when you're doing these exam questions, when you're dealing with things with magnetic fields, which are 3D, is to take out some pens and then basically put it in front of you. So here you go. Your magnetic field is into the page. So take out a pen and put it in front of you and stick it into the page, right? And then get out another pen to represent the current. And this current is going to lay flat on the page, going diagonally up the hill, diagonally up the page. So you have a pen sticking into the page, and you also have this pen on the page. And if you have it in front of you, it should be pretty clear to you, actually, that it is just going to be perpendicular because it is 3D. You have a 3D plane. Take it this way. You've got another pen, which represents the magnetic field, which is going to be sticking out of the page. So it's vertical, sticking out of the page, whereas this other pen is lying flat, left up on the page. And if you bring the pens together, it's very obvious that they're going to be perpendicular. So in other words, if you take your flat plane, right, which represents our paper, and in my case here, my magnetic field is just going into the page. I'm looking at it from the top. This is my perspective. I'm looking from the top. And so all my magnetic fields are just going into the page and out the other side. Then it doesn't matter how I place my pen on this page. I could do it that way, and it's going to be perpendicular. I could do it this way, and it's going to be perpendicular, right? It doesn't matter how I do it. No matter how I do it, it's going to be exactly the same. I could place it that way, and that's going to do something like that on that page. But no matter how I rotate my pen on that sheet of paper, the fact of the matter is the magnetic field is going straight down. And so any pen on this piece of paper, no matter how I rotate it, as many times as I like, to any angle I like, as long as it stays on that page, it will be perpendicular to the magnetic field. And so for that reason, I can draw any conductor in any direction I like on this page, and all of them, without fail, will be perpendicular to this magnetic field because the magnetic field is not on this plane. It is perpendicular to it and going straight directly into the page. And that is why, for these situations, theta is 90. When you come across these situations, theta is not 90, and then you need to worry about it, but otherwise theta is 90. And that's something important that you need to consider.